really pleased, excuse me, to introduce Charles P.T. O'Dell, and he has spent 30 years in the regular and reserve Navy. And on top of that, he's been a member of the Royal Astronomical Society since 1973, where he's held a number of executive positions. And he received the Royal Astronomical Society of Canada 2017 Service Award. Since retirement, Chuck likes to combine his three hobbies: astronomy, flying, and geology. And oh, he also has a sailboat, which he sails on the Ottawa River. His interest in craters began almost 50 years ago, and he's flown his small plane to almost every meteorite crater in Canada, as well as many in the US and as far south as Puerto Rico. He has a website, craterexplorer.ca, where you can find all sorts of interesting information about Chuck and his many craters. So I'll hand it over to you guys, Sheila and Chuck.
All right, thank you very much. So good morning, everybody. I'm Chuck O'Dell, and retired scientist with too much time in his hands. So what do? You get in your airplane and go exploring, I guess. So let's go, Sheila, are the first slides up there? Can everybody see?
They are now.
Okay, great. Okay, that's this is my introduction slide. This is the background, is the Pingula Crater up in northern Quebec. And this was one of my childhood dreams to get to. And you can see, actually you can see the circular, rim of the crater. It's so big, it's a few miles or a few kilometers across. And as I mentioned, it was one of my childhood dreams to get here, and I finally did. And I'll get to it later in my presentation. But what I'm going to do, next slide, Sheila, please. I'm going to show you Canadian craters from top to bottom. So just to give you some background here, as we mentioned, I was regular force Navy, and then in the reserve, I was electronic warfare and got into electronics, and then in the high-tech field. And on the left-hand side there, that's a picture of me 25 years ago in front of my electron microscope. I was in semiconductor failure analysis. On the upper right is a picture of me in my airplane at Puerto Rico, just over the Arecibo radio telescope. So all my interests in one page pretty well there: geology, flying, and high tech. Lots of fun. Next slide, Sheila, please. So I'm going to start showing you the craters I've explored in Canada. I'm going to start from the west coast and work my way east. But I wanted to show you this picture first. This was the ice age in Canada. So where the white is pretty well where we had kilometers thick ice scraping over the land. And it virtually scraped off all the soil. So underneath that ice pack is basically bedrock, bare bedrock. And the craters are very exposed there. In the gray area, of course, is the prairies, kilometers thick soil, and so on. The craters are there, but they're buried, and I'll explain how we discovered those later. And next slide, Phil. I'm going to show you how a crater is formed first, and then we'll get into what we're seeing here. So what we're looking at is a bolide that hit Earth. They're hitting at 14 to up to 80 kilometers per second. Now that is a lot of energy. So the amount of energy increases exponentially as its speed. So when a bolide does hit the planet, you have to think of, if you stick your thumb in some cookie dough, you make a hole. Basically that bolide, with the energy it hits the Earth, the rocks are essentially a liquid at those energies. So the bolide actually penetrates the planet, and then the energy release from the compression, etc., from that impact causes the explosion. And the second part on the left there in the center, you can see the explosion that caused the original crater. Now, you look at all the craters on the moon and they're all circular. And you think, well, gee, they all must have hit at 90-degree angles. No, what causes the circular effect is the penetration of the bolide and then the explosion. And the explosion causes the circular crater. There are craters that are more oval shape, and this is when you have a very low impact angle. So, you know, a couple of degrees, and what happens is you get an oval type crater with the explosion. But majority of them, most of them are circular. The bottom slide shows the evolution after the impact. So the first two parts of that happens in a millisecond and a microsecond. And then what you have is the hole in the ground that gradually erodes and shuffles around, earthquakes and so on because of it. And what you get is the slumping. If you look at the picture on the right, that is, you see the edge of the crater there, it looks like there's a bunch of avalanches around it. That's because the rock was unstable on the impact. And of course you get slumping inside the crater. If you've probably seen videos of raindrops hitting a puddle, and eventually, you know, the puddle starts at a crater, then you get this center reflex back. And you see the center peak, the central peak inside that crater is essentially the same thing, is the reflex back of the rocks on the impact. There's so much energy that happens that the rocks actually look, you know, for a millisecond are almost a liquid. So this is how a crater is formed and why they're always circular. So let's start exploring. So the next slide, Sheila. We're going to start on, you're looking at, oh yeah, these are all the Canadian craters. This was published in the Royal Astronomical Society manual, years and years ago. So I keep that as my, my slide. So you can see the size of the craters over Canada. There's little wee dots on the bottom versus big circles on the top. They're kind of cool. And yeah. Some craters are side by side. If you look on the upper left, that's Sudbury and Wanapatei right beside it. There are two impact craters side by side, but one happened a billion years after, a billion B with a B, after the Sudbury impact. I'll get into that later. And in the center, you see two craters side by side. And for years and years, scientists have thought this had to be a double impact. Two asteroids orbiting each other or something like that impacted at the same time. But no, these craters happened hundreds of millions of years apart. And it's just coincident that they're side by side. It's kind of cool when you think of it. Anyway, that's kind of a list of the Canadian craters we're going to see virtually as we go through. So next slide, Sheila. We're going to start on the west coast in Alberta, and this is the White Cork Crater. And this was a hole in the ground that hunters knew about for years and years. In the spring, it's full of water, and then it evaporated or drained out and so on. And it wasn't until the last 15 years or so that somebody found a meteorite close to it. And in the bottom center, you see a picture of a meteorite that was found actually at that crater that I own. This is my personal meteorite. And so on the top center, you see, this is called LIDAR, laser, just like radar, except there's lasers that impact through the trees and they eliminate all the tree attenuation and so on. You just have the ground reflections. And so they've discovered this circular object looked like a crater. So we investigated, and sure enough, there's piles of meteorites around it. So it's been pretty well fished out for meteorites now, but this is how this circular object was identified as an impact crater. There are piles of circular objects throughout Canada. I've explored a lot of them, but you have to have exact proof of, in fact, it was an impact. Finding a meteorite beside it is definite proof. In fact, it is an impact. And in the right is a picture of myself with Jillian. She's explored a lot of craters with me. I have a lady that's just as fascinated as I am of going through impact craters. It's kind of cool. Okay, next slide, please. Now we're looking at Pilot Lake. It's right between Great Slave Lake and Lake Athabasca. It's called Pilot Lake because the bush pilots, as they're flying around, there's hardly any landmarks, but this big circular lake is a definite landmark. So when they find that lake, they know exactly where they are. That's why it's called Pilot Lake. And it hasn't been until, the last 25 years or so that it was in fact identified as an impact. So how did they identify it? Well, there's two things. In the top images, you see the one on the extreme left on the top, that's called a planar deformation. This is quartz crystal that is cracked in a specific way of a high energy, either a high energy impact or a nuclear explosion. So we're pretty sure that that hole wasn't caused by a nuclear explosion. So this is called a planar deformation feature, which is a definite impact identifier. Just beside it, with my geological hammer, is a rock with rocks inside a rock. This is called a breccia, an impact breccia. Now, there are many kinds of breccias that are caused naturally, and there's some that are caused by impacts. This is why it's an impact breccia. So a breccia is kind of proof, but you have to verify that in fact there is impact melt rocks around this breccia, and it takes a little bit more than a visual inspection to see it. So anyway, this is Pilot Lake up in just south of the Northwest Territories. We flew up there. Actually, on that trip, you can see the wing of my airplane in the image there. And Jillian and I flew all the way up to the across the Arctic Circle, up to the Arctic Ocean, and put our feet in the water up there, following the Mackenzie River. That was, if you have a chance to see the Mackenzie River, it is one of the most beautiful aspects of Canada you'll ever see. It's just awesome. Anyway, we were very privileged to see it from the air. Okay, next slide, please. So we're getting down just beside, let's see now, we're right below Lake Athabasca. And below Lake Athabasca on the image on your right there is the sand dunes around Lake Athabasca. This essentially is the sand that's deposited, and the oil sands are inside that group, that vast desert of sand there. And of course, there's an impact crater right in the middle of it. Unfortunately, it's buried, so you can't see it, but it is there because drilling through that area, they found these planar deformation features, which in fact did confirm it was impact. And with the geophysical echoing through the ground, they can actually see the crater impact image. In the center top, if you look closely, you'll see a small circle. It's not very visible, but that's the center of the impact. So basically in the center of that image is where that crater happened. So just below Lake Athabasca, just as you can see, we're having a great time exploring Canada and seeing craters at the same time. So next slide, Sheila, please. So just north Saskatchewan. Now in the picture on the left, that's a map of Saskatchewan with a planar deformation feature image in the center of it. So you can see just below the Carswell crater is the Gow Lake crater. It is a central peak. Well, I want to mention as well, each image that you see, I've identified how big it is. Gow, you can see, is 5 kilometers across. It is a complex crater. Actually, Sheila, can you go back? Let's go back until we see the picture of where we had the impacts. Can we, I want to just go back, keep going, I'll tell you when to stop. Stop right there, please. Oh, back one down, please. Okay, we have, one more, please. There are various classifications of impact craters. There's complex. These are circular craters with the central peak in it, like the image we saw before. And they're simple, just bowl-shaped. And then there's all kinds of different, I'd say, classes in between. But complex, central peak, and simple are the kind of craters that we're going to see today. So I just want to identify that. So when you go through our images, you're going to see that I've, on each slide, you'll see the identification of the crater, the size of it, the type of it, and this is the type I mentioned, complex or simple, and how old it is. Just go down one more slide, please. Okay, that's White Court, and I just want to mention that's in the Holocene. That's when it happened around the time the Battle of Hastings. It gives you an idea of the time of that one. Down to Pilot Lake, the next one. This is in the Ordovication period. This is where all life was just in the ocean. So basically the land was barren. So let's go on to Carswell, the next one. And this happened in the Cretaceous. You can see 115 million years ago. This is when Pangea split and the dinosaurs are dominating. So gives you an idea of the age spectrum that we're going to see throughout the next one. So let's go down finally to Gao. Next one, there we go. And this happened in the Triassic. This is the age of reptiles. So it gives you an idea. So you saw that picture of the moon, a circular crater with the central peak. Well, Gao, this is a very small crater with a central peak in it, full of water, of course. But that is an impact, and it was identified by the planar deformation features. Next slide, Sheila. This one here is Deep Bay in northern Saskatchewan. It's called Deep Bay because it's the deepest lake in Saskatchewan. It's 220 meters deep. It has no islands in it, and it has a sedimentary rock floor. So it's a simple crater, but it's a flat floored crater. Basically, it's simple, but it doesn't have the bowl shape. It has a flat floor, and it's full of sedimentary rock. And this is basically, what was it? Created in the 99 million years ago. So it's, you know, fairly old. Back to the dinosaurs were still there. And of course, we had this impact of the dinosaurs around. So I imagine they were thinking, well, if we had started a space industry, they might have stopped the big asteroid that hit them and caused their extinction. But unfortunately, they didn't. So they were extinct. I just want to mention this, the Saskatchewan map on your left. You see the yellow, that is sand, and the pink is the bedrock. So Gao and Deep Bay were basically in the bedrock. That's why you can see the crater formations of themselves. At the bottom of the map of Saskatchewan, you're going to see 4 craters, but they're buried under kilometers of ground. So next slide, Sheila, and I'll explain it to you. So the bottom of the map of Saskatchewan, you see my 4 craters that we explored over. Essentially what I did, I just flew over them and took a picture of the exact impact point. There, it's just prairie, you don't see it, but underground, through geophysical evidence, we do see a circular crater feature. And you can see that most of them, actually the first 3, have planar deformation features, which does cause, what's the difference between a meteorite? Okay, so somebody just asked me the difference between a meteorite and an asteroid. Okay, I'm going to give it just diverge for a second. So you have an asteroid. This is a rock that's flying around in space. This is an asteroid that's out there. Now, if it's small enough and it hits the atmosphere, you'll see this bright meteorite trail, then it just evaporates basically. That's called a meteor. If that meteor now is large enough to hit the ground, it's called a meteorite. So, if you look at my image, this here is a meteorite. That is a rock from outer space that I've kept. This is my little hobby of keeping rocks from outer space. It's kind of cool. So that is a rock that was from outer space. It did not burn up in the atmosphere, which would have been a meteorite. It hit the earth, it's a meteorite. That's the difference between them all. So a rock in outer space is basically a piece of an asteroid. So let's go back. Okay, so the first 3, you can see we're all identified of these ones, Elbow, Maple Creek, and Viewfield. Were all identified by planar deformation features. They drilled it, found a quartz crystal, and looked at it microscopically and saw the planar deformation features within it. The bottom one, Dumas, it has not been firmly identified as an impact yet. It has all the characteristics, circular, it has the bowl shape, et cetera, but we have not found defining features on the fact that it was an impact. That's why I put an asterisk beside it. And this asterisk you'll see further on in our presentation. Basically, I designated it as a probable. And basically, Dumas had happened in the Pangea when the dinosaurs are still dominating there. So next one, Sheila, we're going into Manitoba. We're very slowly heading east. And again, this is St. Martin. It is under kilometers of soil again within the prairies. But again, geophysical analysis has determined that in fact it is an impact site. It's a central peak impact site. It's a complex crater. I think, yeah, it's complex. 40 kilometers across is a big one. But just on the north of the crater, north of St. Martin, there's this river called the Dauphin River. And the image on the upper right, that you can see the river comes up and does a 180-degree turn. This is not a normal turn of the river. Basically, you know, you see them, they have these twists and turns as they go through the river. But this is definitely a 180-degree turn. So the Dauphin River actually was influenced by the crater rim itself, which caused it to cause an 180-degree turn. This is strictly hypothesis right now, but I'm pretty sure that this is what caused it. The St. Martin, it happened in the Cretaceous a long time ago, 227 million years ago. That's how long it takes for our solar system to orbit once around our galaxy, just to give you a feeling of how much time had passed since this crater happened. And the dinosaurs, again, are still dominating here. So let's head down to the next slide, please, West Hawk. This, again, is still just in the bedrock now. You're just getting out of the prairies into the bedrock, and you can see that two things identified this. One is the planar deformation features, and it's a gravity anomaly. Basically, you can do gravity searches over the prairies and the planet, and you can see these circular indicators of the gravity concentrations. And this is caused by, within the crater, when it impacts, it sort of impacts, it crushes up the bedrock. And you don't have solid rock anymore. You have a mishmash of rock, which decreases the gravity signature. And the more the rock is pulverized, the smaller the gravity signature. And the smallest gravity signature is in the center of the crater. So you can see the various degrees of gravity measurements as we go out, and they happen to be circular, and that's another indicator of an impact. It is, again, the whole of Canada now has been documented with gravity measurements and so on. It's kind of neat, and they can actually see the circular patterns. So when you see a circular pattern under the ground, that's another way of looking. Well, let's drill there to see if we can find a planar deformation feature or something. Okay, let's go to the next one. We're getting into Ontario now. And in Lake Superior, and the northern shore of Lake Superior, there's a series of islands called the Slate Islands. The Slate Islands are actually a center peak of a large crater. If you look closely at a map of the north shore of Lake Superior, find the Slate Islands, and then the north coast of Lake Superior, you can actually see the circular crater rim of the edge of the crater itself. It's all underwater, of course, but again, by sonar profiles, we did, in fact, document the fact that it is an impact. Within Slate, sorry, that was my phone here. There we go. I'm going to, there we go. Okay. Where was I? Okay, there's the largest shatter cone within the crater itself. Another way of identifying an impact crater is a shatter cone. Now I'm going to show this up very close. I don't know if you can see it there. Here we go. Here you can see the stripes on that rock. That is caused by the energy of the impact. It's very, very unique to impact craters. And this is another way of, in fact, identifying an impact is by shatter cones. And we have a very cool story coming up that, that includes a shadow cone that I'm going to show you very shortly. But Slate Island has been identified by this shadow cone effect by these guys here. You can see the rock again with the stripes on it. If you ever go through the bush and you see a rock with stripes on it like that, let me know. You just might have found an impact crater and you'll be famous. If you look at the bottom left, that's the largest shadow cone on Slate Island. It's probably the largest one on the planet. If you see in the center, there's a little white dot. That's me standing there on my t-shirt. That's how big that shadow cone is. That was a neat exploration time we did there. And then of course, there's lots of breccia in Slate Island. So that's another way of finding the fact that it is an impact crater. So again, shadow cone and breccia for Slate Island. This happened in the Silurian. The temperature at this point was 3 degrees higher than what it is now. And the oceans were 180 meters taller. This is what, 400 million years ago. That was kind of cool. Okay, next slide, Sheila. We're getting into Sudbury. Now, Sudbury is very unique. It's 1.8 billion years old. B with a billion, with a B. It is not circular anymore. It is so old that the geological features within the Canadian province, there are many geological continents that actually collided within our province. And it actually made the circular Sudbury crater into an oval, as you can see there. In the upper right picture, you can see, there we go. In the upper right picture, you can see the Sudbury crater itself. It's very, from the air, it's not, how should I say, immediately identified as a crater, but throughout identification of shadow cones within it, planar deformation features, and breccia, it has been identified as, in fact, a crater. Down underneath Sudbury, of course, there's mine shafts going left, right, up and down. If you put them length to length, they go from Vancouver to Halifax. That's how many shafts are in there. It's so honeycombed that we think it might collapse with a major earthquake, who knows. But just if you look at, again, in the upper left image, you can see a lake just north of Sudbury Crater. That's another impact crater I'm going to get to in a second. But I just want to let you know that this happened, 1.8 billion years ago when oxygen was first appearing on our planet. So this was a long time ago, long time ago. And next slide, Sheila. Right in the upper, just north, if you look in the upper left-hand image again, you see the Sudbury Crater and the lake just to the north of it. That's the Wanapatei Crater. That one was identified by many means, the gravity anomaly, the planar deformation features, and another feature called a suivite. If you look in the upper right, that's an image of a suivite. And that was drilled out of the Wanapatei Crater, and it's part of my collection of various rocks and craters. It's one of my passions is collecting many rocks and craters. So again, that was identified as a very as a simple crater, and the gravity features made it circular. The planar deformation features definitely confirmed that it was. And right, this happened in the Eocene, it's called, the dawn of the major fauna. The fauna was just coming onto our planet at this time. Okay, next slide, Sheila. We're getting into the Brent Crater, just north of Ottawa here. It's if you ever want to spend a day drive in exploration, take a drive up north to the Brent Crater. If you go on my website, you'll find directions how to exactly get there and actually see an impact crater. It is really, really neat. It was discovered. Now, in the very, very first picture, my cover picture, I showed you the Pingula Crater way up northern Quebec. When that was identified as an impact, the Geological Society decided, well, let's go through Canada and find out all these circular objects and features, and let's see if they are craters. And in fact, this is how Brent was eventually identified as an impact crater. They flew over it, saw this circular feature, did a gravity feature on it, and of course it was a circular. They drilled it, found breccia, planar deformation features. So the breccia is an image on just in the center top there. That's a picture of the breccia that I found within the crater. It's kind of cool. And there's my airplane wing just circling over the crater itself. It's, again, bush pilots flew over that for years and years, not realizing that fact that it was an impact crater. So that's very, very close to Ottawa. So as we're getting close to Ottawa, I'm just going to show you a fact. If you drive a straight line for one day from Ottawa, that's sort of like the radius of a circle. Make that radius into a circle. So within that circle, there are 10 impact craters that you could explore. That's how many impact craters there are around here. A lot of people don't know that. It's kind of neat. So anyway, next slide. We're just south of Ottawa now. We're getting into the Hollerford Crater. Again, this was just there's a road right through it for years and years. People went up a hill, down a hill, through the crater, up the hill on the other side, not realizing exactly what it was. And since the identification of the Pingula Crater, they have since identified definitely this as an impact by the planar deformation features from the drilling of it. This is actually about an hour's drive just south of Ottawa, and it's a very pleasant drive. Again, from my website, there's exact directions on how to get there, and it's kind of unique to actually park, stop the car on the top of the hill and look, and you can actually look into an impact crater. Not too many people realize that, in fact, it is an impact crater. It's kind of neat. And I did a tour of the Royal Astronomical Society when we had our GA here, the General Assembly, and I took maybe 75 people through a tour of it, and it was very successful. We had a great time, and walking through the crater and so on. So anyway, this happened in the Proterozoic. Again, the first appearance of oxygen on our planet. There's no complex life. So this was an old crater. And actually, this was buried by limestone over the ages. And around the rim, there are a lot of limestone cliffs from rock cuts going through. So the limestone is post-impact. It was deposited after the impact. So when you see the limestone there, just realize that, no, that was not there on the impact. The limestone is from the oceans that buried this area years and years, millions, hundreds of millions of years ago. So let's head a little bit further east now to Charlevoix. Next slide, Cheryl, please. This here is just east of Quebec City. And I mentioned the shatter cone. So the bottom right image, you see my finger pointing at the shatter cone in the bedrock within the crater. Now, I guess 30, 40 years ago, road crew were going through making a rock cut in this area to make the road a little bit straighter so it didn't have to go over the hill and so on. And somebody realized, hey, there's these crazy patterns on the rock. Better call a geologist in to find out what exactly this is. Well, what it was, he identified, in fact, is a shatter cone. And it was from that they realized that the Charlevoix area is a large impact crater. It is, what, 54 kilometers across. It is big. So you see the picture of me standing at the Charlevoix airport with my airplane in the background there. And just over my left shoulder, you can see the central peak. That hill there, that's the central peak within the crater. So here I am standing within an impact crater. Again, for hundreds of years, people were going through this area not realizing exactly what it was. There is a big geological story about this. I won't get into it now. It is another lecture that I can spend an hour on, but if you get into my website, to the Charlevoix, you'll see how fascinating this area is. It's really, really neat, really neat. Okay, so we're in my airplane from Charlevoix. Now we're heading north into Quebec. Next slide, Sheila. Up on Lake Mastastany, way up north there. In the middle, there's this little wee island, and this is called Île Relou. identified as an impact by the shatter cones on the bottom left. You can see the image of a shatter cone there, and the planar deformation features. So again, definitely an impact. The island itself is a small center peak. So we did classify this as a very small central peak impact crater. So the island in the foreground, between the island and the Île Rouge, the water there, you can see the circular coast of that island around it. That is the edge of the crater rim of the Île Rouge. We paddled up there, and it was a long paddle, actually. It took us a day to get up there in a canoe, and we explored it, then another day back. So we spent, about 3 or 4 days up there. It was a very neat exploration trip. A very close friend of mine, he owns a canoe, I owned an airplane, and between the two of us, we explored lots of craters. So this was one area that you had to have a boat or a canoe to get into, and we paddled up there and actually saw it. It was a very neat adventure. Next slide, Sheila. So just south of Île Rouge is Preschio. It's another impact crater that we explored by canoe. This is a complex crater. It may have had a central peak. We don't know, because over 1 kilometer of rock has been eroded from this area since its impact. And we're looking at what, over 500 million years. So the solar system has gone around the galaxy twice after this impact had happened. So that's a long, long time ago. So essentially what you're looking at under the wing of my airplane there is the bottom of the crater, essentially. The bottom of the bowl of the crater itself, with the central peak that has been eroded away in the middle. So that island. So on the upper left of the image, you'll see a picture of me holding a shatter cone. Now, I'm going to tell you a story about this. Again, Eric and I, my buddy, we canoed into the lake here, and canoed quite far, actually. One day we're paddling in the middle, just in the back area of the lake there. And the blackest cloud you ever seen in your life, major storm coming towards us. We thought, holy mackerel, we can't get back to the tent now, it's too late. So we paddled like heck to get into the lee of an island, and the storm came down. It was horizontal rain for about a half an hour. It was just totally awesome, but we were safe. We were tied up beside this island. So we were sitting there talking about life, the universe, and everything. And my buddy Eric said, hey, Chuck, I see a shatter cone. I said, no, you're just kidding me. So anyway, but 2 minutes later, I said, the heck with this. I'm soaking wet now. We're soaking wet from the rain. I got out and I said, I'll just walk around and explore the island a bit. So the first rock I picked up, believe it or not, was a shatter cone. That was it right there in my hand. You can see the pattern of the shattered rock itself. So again, that's another part of my collection. And within drilling within the crater itself, they found planar deformation features as well. So that again identified definitely as a crater. But it is an old crater, you can see. Okay, next slide. We're getting into now Manicouagan. If you look on a map of Quebec, you'll see this big circular lake. That is a large impact crater within the bedrock, the Precambrian bedrock. Again, it's 214 million years old, just around the time that we did one orbit of the solar system. Identified by shatter cones, the upper left, and the planar deformation features. So the center island, the circular island there, you see the island, that's pretty well all impact melt. This is the central peak of the thing that poked up. Now, you realize, well, why is there a circular lake around it? Why is there not just a lake? Well, when the impact happened, what you have is the impact that caused the rock to first evaporate, to melt away, pulverize, then shatter, then eventually just crack open and so on. So as we drove up towards the Charlevoix crater, you can actually see within the rock cuts itself. First of all, it was solid rock, then the rock started to crack and then pulverize and so on. So you can actually see the stages of the impact energy as we get closer to the crater. So the circular lake itself This was the area where the rock was pulverized very, very small, and the glaciers had actually scooped out these small shards of rock, which caused this circular lake, which from the Charlevoix or the Manicouagan Dam caused it to fill up. And so that's why we have a circular lake, and we did explore right into it. This is a picture from the space shuttle, actually. That's how high that image is. So the story of the picture on the bottom right, we had canoed into the crater, we explored, and we had a canoe full of rocks, and we're heading back out. And you can see in the background, see all the white caps on the water there? Within, I'd say, a half an hour, the lake, that lake went from dead calm to, I'll say the waves themselves maybe 2.5 meters high. And here we were in a canoe full of rocks in the middle of a lake. What could possibly go wrong there? So we actually made it. Where we are on right now is an island in the middle of the lake. If you look in the circular image from the space shuttle in the bottom of the circle, you can see some islands dotted there. One of those islands is where we were marooned. We got on that island and we were actually marooned there. We couldn't get off because of the water. We had enough food, we were okay. But we got on the island, we started a fire and dried off because we were soaking wet from the spray and everything. And we waited the day, it didn't clear, so we picked our tents and that. So about 3 o'clock in the morning, Eric woke up and saw the wind had died. So within 15 minutes, we had struck camp, got in the canoe and paddling like heck to the other shore. So within about 4 hours of that being marooned, we were sitting in a restaurant having bacon and eggs and a coffee thinking, you know, 4 hours ago, we were marooned. We didn't know how long we were going to be on that island. So that's what it takes to explore these things. It's kind of neat. So yeah, this happened in the Triassic. The dinosaurs, the mammals, the amphibians, and the reptiles were all battling at that time to be in the top of the food chain. So it was kind of a major battle at that time. Okay, next slide. We're going further north now. Again, at the very beginning, I mentioned these two craters, the Clearwater Craters, and they happen side by side. But if you look at the dates, one happened 460 million years ago, one happened almost 300 million years ago. So they're 100 million years apart. One is classified, the one in the, if you look in the right-hand image, the two craters there, the one with the circle in the middle of it, that is a circular peak. So in other words, the peak peaked and then collapsed within itself, caused these circular islands within the crater itself. So they are both complex craters, happened many, many years ago, identified by planar deformation features. If you look at just under my wing in the picture on the left there, that is the barrier between the two craters. It was kind of neat. The two craters, the two lakes on each side of the barrier identified each impact. And that's kind of a unique picture of the crater rim. Basically a dual crater rim, one on each side. It's kind of neat. And again, you can see on the bottom right is the profile, the geological profile of the two craters. So the detailed geological story of these craters are all documented on my website. So if you have an hour to kill, go on in there and take a look. It's kind of neat. Okay, next one, we're going further north now in northern Quebec, up to Lake Couture. This one was identified by planar deformation features, and there were shatter cones here as well. It's an old one, it's an old lake back in the Silurian. Again, the oceans were almost 200 meters higher than they are now. This is after the dinosaur extinction, 42 million years ago. So yeah, but I don't know if there's any life up there in northern Quebec, who knows? Lots happened. But the bedrock, any fossils in that, of course, the glaciers at this point had virtually scraped all the soil off the rock. So what you're looking at in the image on the bottom there is strictly bedrock and a big circular lake. What is it, 8 kilometers across? It's kind of a big one. So well, a little bit higher now, next slide. we're going up to the Pingula Crater. This is my dream come true. We actually explored around this crater. My first exploration of it, we flew up over it in the center top image there under the wing of my airplane, the circular lake, and boy, oh boy, that was a dream come true. But Eric and I actually explored that crater. We actually went up, had a charter flight up there and spent almost a week exploring around there. And we found impact melt. This is how this crater was in fact identified finally as an impact. The story of this, I mentioned earlier, I saw this first on Front Page Challenge. And on Front Page Challenge, Dr. Mean from the Royal Ontario Museum documented exploring this crater. He did not find definite proof, but they thought it was a diamond mine, a kimberlite type of thing. And the Chubb, the geologist, thought it was a kimberlite mine, and he was going to be rich finding diamonds up there, but of course they never found any diamonds. And they didn't find any identifier for an impact. It wasn't until the late 70s, I think, they finally found impact melt around that. On the upper right, Eric is holding up a rock, an impact melt rock that happened from the crater. So on the impact, you can see that hole in the ground there was caused within a millisecond. So you could just imagine the energy that caused that thing. And this was only 1.5 million years ago, so it wasn't that long ago. So these things do happen. They happen. It's not a case of if, it's a case of when the next one's going to hit. So if we don't have a defense set up, we're going to get hit with one. Yeah, who knows? But okay, so from there, that's about as far north as we got with the airplane. The next one, we went down to Lake Monterey, just south of the Pingulate. Again, you can see the glaciers had scraped the rocks off completely. It's all bedrock there, circular lake, and identified by planar deformation features. So again, I just had to identify or fly over these craters and take a picture of them. So there we go, all the way through. So the next one, further south now, we're getting down to Lake Mistastin. This is a Central Peak Basin. So in the upper right image, it's hard to see, but actually what we're doing, we're flying into a large basin. Those clouds are just grazing the crater rim. So we had to get over the rim down into the crater to fly around and then back out of it again. Those clouds were pretty low. It was kind of a neat day to get in there. But again, it was identified by planar deformation features. And it's in Labrador there. You can see right almost on the Atlantic coast. But that cliff on the bottom right, that image there, that cliff is all impact melt. So basically, it is the melt from the impact, and the glaciers have eroded it away, and there's just that one area left that's left there. Again, this is just the dawn of the new fauna, basically, when this happened. It's 36 million years ago. So the mammals were almost at the top of the food chain at this point, and here we are, I guess, eh? So next slide. So we're getting into now, just off the east coast, Montagna complex crater. This happened in the ocean. So of course I couldn't fly out over the ocean just to take a picture of the area. So I took a picture from the coast of Nova Scotia at Shag Harbor there. And again, it was identified by the gravity anomaly just over the area by the oil drillers and so on. They extensively studied and so on. And you can see in the bottom is the geophysical profile of it. This is how they did find that, yeah, it is, they haven't recovered any shatter cones or planar deformation features, but they're absolutely sure that it is an impact just because of the large structure and the various characteristics of it. So next one now, we're getting into back to 12,000 years ago. Something weird happened on our planet. There was a population called the Clovis people, They were a very high technology Stone Age, a race of First Nations here that pretty well dominated the area. They, from coast to coast, they pretty well dominated the area. And you can see from the arrowhead, the technology they had and so on. That image on the right now, that black line, that identifies a geological feature we're still studying. It is kind of cool. So at that line, below that line, there is lots of energy or lots of evidence of the Clovis people. Above that line, there's absolutely no evidence of the Clovis people. So there is a very large scientific conundrum of exactly what happened there. So there are hypotheses that there is, in fact, impact craters that might explain this 12,000-year-old extinction event that happened here on our planet, right here where we're living right now. So next slide, I'll just go through a couple of craters that we think might have occurred at that time that might have influenced it. So in Nova Scotia, we have an area called the Bloody Creek. Again, this is a probable crater. We don't have any firm identifying features of it, but it has been extensively studied by the University in Nova Scotia. And they're absolutely convinced it is impact, but we haven't found absolute proof of it yet. So there is one crater that happened possibly around that 12,000-year time frame. Next slide. Just south of Sept-Îles, in the St. Lawrence, Gulf of St. Lawrence, there's this crater, again, underwater, no firm identifier proof yet. We haven't drilled there yet or studied it firmly, but the profile itself almost firmly identifies it as an impact. And this impact could have happened right at that 12,000-year time. So again, this is a mystery, who knows? So next slide, getting closer to home. Just south of Kingston, in Lake Ontario, is a thing called Charity Shoal. Again, a very circular object. We think it's a crater, but we don't have any firm evidence. Being in Lake Ontario, of course, we can't drill because of environmental features and so on. We just don't know what we're going to hit down there. So it has been studied with geophys and so on, but no firm evidence that it is an impact. But that circular object sure looks interesting, doesn't it? Again, this could have happened right at the 12,000-year time frame. So that's a mystery. And final, one more slide, next slide. We're going back up to northern Quebec, just south of the Pingula Crater. Again, there's this circular object. Look at that. That has to be an impact crater. But there is absolutely no proof that it is. And there are a lot of geological features that could explain that circular feature. So, oh boy, who knows? Who knows? It is a mystery. It is a conundrum, but it could have happened within, that would have been under the ice cap itself. So whatever happened there, the bolide would have had to penetrate the ice to make a hole in the bedrock. So there's all kinds of hypotheses. It could be a sinkhole. We don't know. We don't know. So in conclusion, let's hit the next slide. So all kinds of comments are whizzing by it, left, right, and center. This is a quote from Isaac Asimov. I always like this. How bright and beautiful a comet is as it flies past our comet. And lately, we've seen 2 or 3 comets in the sky. If you subscribe to the Royal Astronomical Society, we will give you details on all the comets that are coming by. There's one out there now. It's not visible by a naked eye. You need a telescope, but it is close by our planet right now. But the point is, here's these comets flying by our planet, left, right, and center. Next slide. Let's just hope they do keep flying by us, not hit us. That crater there, that's the Arizona crater. And there's a long history with that. Again, I could talk another hour about this crater itself. It's actually a square crater. And if you want to find out why it's square, get into my website and explore. It is kind of neat. But let's just hope these comets still keep flying by us and not hitting us. So at that, I'll conclude. And if anybody has any questions, I'd love to answer them.